This lesson's on nuclear fusion. Nuclear fusion is essentially a process where two nuclei and small nuclei combine to form a single nucleus. Okay, so we might have, for instance, now I've got the red balls as set as protons here. So this is a proton and another proton. And if I give them enough kinetic energy, excite them enough and give them enough kinetic energy toward each other, they will come very close to each other, but they won't quite touch. There's an electrostatic repulsion, of course, which almost forbids them to come in contact. Electrostatic repulsion. And so, so it's very hard to get these things to collide. If, of course, we're in a star, then the pressures and the temperatures are high enough that we can get them to collide. If we get them close enough, then the short range nuclear force overtakes, or rather takes hold. Nuclear force, yeah, so it can take hold. So we can get this situation here. Do that. C. Let's have two. Oh, I'm not going to be able to do that, am I? Because they won't become close. Oh, yeah, okay, that's no good. That's all right. Imagine though, I've brought them so close to each other that they kind of fuse together. Okay. Okay, so that is possible. The short-range nuclear force can take over. The electrostatic repulsion, trying to drive them apart, doesn't do so. I've prepared a neutron here. Don't worry about the green ball at the moment. This is just a neutron that doesn't matter so much. That matters for later. So fusion, where I fuse two nuclei together. Fusion. They're kind of bound together. You can think of that like a chemistry, a chemical uh, uh, binding together. Now these would be atoms in chemistry, of course. If you saw these in chemistry, we're looking at these being nuclei or protons in the nucleus. A nuclear reaction where we have energy released is where the products have less mass than the reactants. So in a fusion reaction, reactants will have greater mass than the products. Let's do an example. Got one here somewhere. Yes, here. So calculate the energy emitted when the following fusion reaction takes place. So we've got deuterium and deuterium coming together to form a helium-3 nucleus plus a neutron. That's quite a different situation to what we saw here. Of course, this is just a very simple situation of two protons coming together. Let me get some pictures. I'll just pause for a second and come back with some pictures. I can't find any pictures. I'll just draw them. That's fine. I can't find any suitable pictures. Let's see, hydrogen 2. So we have a proton, and I'll draw the other proton here, and a neutron. So we have deuterium, plus deuterium reacting to form, not chemical reaction, a nuclear reaction to form helium-3. So we'd have two protons in the nucleus because it's helium, and we'd have a neutron as well. What's happened to the other neutron? Well, that's kind of gone, oh, yeah. That's right. So they're saying that the neutron has basically gone off by itself, flown off. This is a reaction that we might see, not necessarily that we're going to see. So deuterium, helium-3, 3 to helium, plus a neutron, mass number 1, charge 0, and this is hydrogen 2, or deuterium, same thing. And the mass of the reactants, so mass of reactants equals 6.688 by 10 to the minus 27 kilograms. And mass of the products equals 6.683 10 to the minus 27 kilograms. Mass of the product is less than the mass of the reactant, so we have energy is released in this reaction. How do we find the mass defect? Delta M, mass defect, which equals these two numbers, 6.688 by 10 to the minus 27 kilograms minus 6.683 10 to the minus 27 kilograms. Divided by 10 to the minus 0 by 10 to the minus 29 kilograms. Energy released, E equals mc squared. Ten to the minus 29 multiplied by 9 by 10 to the power of 16. Answer is 4.5 by 10 to the minus 13. Joules. Joules isn't a unit that we use or we relate to in atomic physics, so we change it to EV, and it works out to be 2.8 million or mega electron volts. So we have one reaction between a deuterium nucleus and a deuterium nucleus, nuclear reaction where they're fused together to form a helium nucleus, helium-3, and a neutron, and we've got 2.8 million electron volts of energy released. This is a massive amount of energy compared to chemical reactions. Okay, so stars. What do they do? It's fusion reactions in the core. or a fusion reactor. So here's an image of our star, the sun, we call the sun. And so it's a fusion reactor essentially. The fusion goes on inside the core where the density is so great and the pressure as a result, the pressure on the atoms that make up the core as a result of that, of the gravity associated with something so massive, is huge. Let's go to a new page. So here it is again. I'll just put it up there again so we know we're talking about the stars. Or our sun rather. We know that fusion goes on in most stars or all stars as far as we can tell. And what it is fusion of hydrogen to form helium. Incidentally, Helios is the sun, and so helium was actually first discovered on the sun using a spectroscope. We didn't know of it beforehand. Helium's what makes up much of the atmosphere of the sun. So what sort of reaction are we looking at? Hydrogen, this proton that we were talking about before, plus another hydrogen, another proton, being fused together. Remember, lots of pressure, lots of kinetic energy to form deuterium, and that deuterium emits at the same time, or rather in this reaction, we have the emission of a beta plus particle, a positron. Okay, so have a look at this. We have a proton and a proton coming together. The number of protons becomes 2, and then the mass number becomes 2 also. But that's not very stable. 2 protons together just by themselves is in fact not stable. They decay via beta decay. So there's a decay, I'll say that here, a decay via beta decay, beta plus decay. So beta plus, what have we got going on? In a beta plus, we have a proton turning into a neutron and a positron being emitted. Okay. Once we have this stuff, then we have another proton come along. This is all in the core of the sun. Seeing our deuterium nucleus, they fuse together. We have enough pressure and enough kinetic energy that they fuse together to form this helium-3. Okay, so proton plus proton, there's only a single proton there, and what we're looking at is, actually I'll draw those so you can see what we're looking at. We have a single proton here, and we have a proton and a neutron here. Proton and a neutron to form 2 protons and a neutron. So there's nothing wrong with that. We don't have to see any decay there. Atomic number 2, mass number 3. That's fine. There's no decays going on. Okay. That's helium-3. Once we've got the helium-3 and we have enough of those around in the core, we see this happen. Helium-3 again. And another helium-3 comes along. They fuse. Fusion occurs to form the helium we know, the isotope of helium that we know, helium-4, 2 protons and 2 neutrons, plus a proton, plus a proton. And the cycle starts again. Okay. So I'll draw those again so you can see what's going on. We have two protons and a neutron. We have two protons and a neutron. We have two protons and two neutrons and a proton and a proton. Better put our neutrons in there. Okay. Show that that is a reaction occurring. Okay. Don't forget here, of course, just as a reminder for those people that are studying at the moment, of course we have the emission of this neutrino as well at the same time. Meter plus decay results in the neutrino for the conservation of momentum. These nuclei are formed in their excited states here, and so we see gamma ray emissions coming off as well as a result of the daughter nuclei being formed in their excited states, gamma ray emissions, and so lots of gamma radiation coming off of the sun, of course. What's going on inside all stars, and this is the most common form, the common state in the universe. Of course, you know solid, liquid, and gas. The star is not any of those things. It's something called plasma. Our stars are mostly made up of matter in state, I'll say state plasma. Not solid, liquid, gas, not fire, plasma. So what is plasma? Essentially, the electrons are stripped. So I'll write this because it's easier than drawing it. Electrons are stripped from atoms. So they don't really belong to anything, leaving, and this is because of the high energies and pressures that we're talking about, or the high energies rather, really. High energies of the atoms that they belong to allow them to go free, and leaving ions, lots of ions, and this is the state plasma. Because of this large mass of the sun is so massive, its gravity is very strong, and so we do need to say, why does it stay, why does this plasma not just float off into space? The plasma is bound to a sphere by the immense gravity of the sun. The last thing, actually we might stop that there for a second.